Before we start, we just want to give you guys a little bit of background on our Center for Cybersecurity and Digital Forensics. We've been around for a while, and among the many things we do, we work on identity management and access control, formal models for computer security, system security, including network, web, mobile, SDN, and clouds. We have also experience working on vulnerability and risk assessment, and as the name of the center says, we also have experience working on digital forensics. We have also had a chance to work with several sponsors and partners. And if you guys are also interested in cybersecurity or one of these topics, if you want to contact us after the meeting, we're always willing to share experiences and support collaborations. So, well, this is our team. As you can see, Josephine, Dr. Simin Sao, and Dr. Gail June Ann. We also have a very nice picture of our rack server. We are proud to run our own cloud in our center, which has a bunch of different servers and CPUs and cores. And this whole thing is actually managed independently from ASU's infrastructure. So before we start, let's talk a little bit about what are the recent challenges here, especially why security compliance is complicated with respect to EDS. First of all, well, we all know that EDS, the nature of EDS is composed of distributed, highly interconnected, and heterogeneous components. Also, we know that EDS should support a continuous reconfiguration in order to respond to on-demand changes. And besides that, also, well, the documents that describe security compliance and best practices are most of the time large, are dense, are difficult to digest, and sometimes they even have conflicts within each other. As a result, well, we have a problem that we may have different subjective interpretations, we may have non-standard implementations, and ultimately, all of these may result in breakdowns between different stakeholders. We also have a chance to participate in a breakout session last March during the CREDC annual industry workshop. And we have here some highlights from that session. People from both industry and academia, we had a chance to talk to each other about what compliance is, how compliance is perceived in the industry. And they said that, well, this is a process that requires considerable effort. Really important, compliance does not necessarily advance security. People see it mostly as a legal exercise in order to avoid fines. Security standards vary significantly from state to state. And then most of the time, actually, compliance is addressed when systems are already designed and already deployed in the field. So there's a need to address those things, the design and installation time. And finally, there's a need also to collect evidence that can be later used for compliance audits. So with this in mind, we are proposing a solution that is intended to fill in the gap between high-level compliance requirements and real-world practical implementations. The idea is that we want to assess that if EDS implementations comply with security compliance requirements. In order to do that, we are proposing a framework for verifying, validating, and attestating EDS. The idea, besides this framework, is that it should be as automated as possible, it should be well-defined, and should allow for some sort of configurations. It should be systematic and well-described. It should be practical, means that it can actually be deployed to actual organizations in the industry. And it should be as non-intrusive as possible. That means that it should represent just minor overhead, and it shouldn't require reconfiguring or redesigning existing systems. So this is graphical depiction of our approach, high-level abstract depiction. The very first thing we want to gather the relevant documents on best practices and security for EDS. Then we plan to analyze those documents. We want to extract the information on security requirements they contain. And we want to represent those requirements by means of ontologies. Then, using those ontologies, these well-defined representations, we plan to create a framework that supports the introduction of software models that can handle automated monitoring, and compliance management, and analysis. The data, later on, data that's going to be extracted directly from EDS infrastructure is to be collected and forwarded to these software models for further processing. As you can see, we have a different multi-layer, multi-plane approach. Now, we can see here pretty much a similar depiction, but this one is mostly focused on the architectural part. Once again, we start by taking a look at documents, analyzing those documents, creating ontologies, and storing those ontologies in a component we call the requirements repository. Later on, we extract, bullet number 3, we extract information from EDS infrastructure. We have some automated tools that can perform this data collection. And then the requirements itself, they're going to be translated into process-driven workflows that are going to be fed with the data we obtain for EDS infrastructure. As a result of this process, we can have automated security monitoring. We can also have analysis of reports that can be obtained from the data and from these processes. And ultimately, number 7, we can have the aggregation of EDS-related documentation. So in order to reduce this approach, we have 3 very important steps. First, we need to analyze the representation of security requirements we have stored in the form of ontologies in order to create what we call compliance workflows. Then, we need to find a way to collect evidence on security relevant data directly from EDS. And later on, we need to have processing models that can implement the compliance workflows I just described, and they can take the security relevant data as an input. So the main purpose and the main goals of this framework would be, first, to allow for analyzing in a very rigorous way the security requirements by leveraging these ontological representations we are proposing. Then we expect this framework, by means of the software models, to allow for continuously monitoring the security of EDS. And we also expect to leverage emerging technologies such as software-defined networks. We plan to automate the process of compliance checks and management as much as possible. And as a long-term goal, we envision this framework to be able to promote the development of security metrics that can be objective, traceable, justifiable, and repeatable as much as possible. So now I'm going to share the microphone with Josie Lamp, and she's going to talk a little bit about how we are now in the process of converting these security relevant or security compliance relevant documents into a repository that is made of ontologies.
Hi, everyone. So I'm also a part of the Center for Cybersecurity and Digital Forensics, and as Carlos mentioned, my focus currently has been looking at our ontological representations. So we wanted to use a standardized and reputable methodology to follow in building our ontology, and for this purpose we utilized OntoArc RE. It's a pretty straightforward process, but it's depicted on this slide. In the first step, similar to before, we are gathering reputable documents from governmental as well as standards organizations, and then in the second step we are identifying the requirements, stakeholders, security controls, and other entities that are relevant to what we're trying to do with this ontology. In the third step, we're classifying and categorizing these concepts and their various relationships amongst each other, and this is sort of forming the structure and basis of the ontology. Next, in the fourth step, we're using hierarchical grouping of our common characteristics to sort of group and organize these different entities into sort of categories that make sense and that can be usable. And in the fifth and final step, we create monitoring and compliance tools that can use the entities and relationships modeled in the ontology towards this purpose of compliance. So among all of the different documentation that's modeled, the level of abstraction varies very greatly. So documents can be very direct, very precise, but they can also be very abstract and high level. And so the ontology tries to cohesively model all of these different levels and all of these different documents. And to give you an example of how this would be actually implemented, we're going to talk about the example of communication channels must be secured between intelligent end devices as well as some other end devices and control servers. So we're starting with the security principle of integrity. Among others, we're focusing on this one for this example. Within one of the security threats that specifically targets the security principle of integrity is system tampering, and the attack vector that would be utilized would be network communications. Some specific attacks related to network communications would be intercept, man-in-the-middle, as well as masquerade. And then to counteract these, we have some different security features and techniques. So we have the feature of a protected channel, and the actual technique that would implement this would be secure sockets layer, as well as this would be implemented on the EDS infrastructure of the MTU control server, the IEDs, and the RTUs. And as you can see at the bottom, we're showing where all of these documents came from and the actual information it was abstracted from. So now this is giving a graphical depiction of how the natural language from the previous slide would be modeled. The boxes are entities, the black arrows are the hierarchical subclass relationships, and the red dotted arrows are the properties or entities that would be modeled between these. We started with the cybersecurity procurement language because it serves as a good starting point. It's pretty broad, but as you can see, it talks about some cybersecurity concepts. So as mentioned before, we have the principle of integrity that is protected by the protected channel of the security feature, and this counteracts the deliberate threat of system tampering. This next document modeled is the IEC 62351 standard, and that specifies some specific types of attack. So as you can see, system tampering is realized as an unauthorized modification attack, and then we have a couple subclass relationships that are very specific types of attack that would do this. This next step is showing the Nist Standard, and it talks about very specific security techniques as well as SCADA system components and configurations. So in this case, we're showing that the security technique of secure sockets layer is implemented by the protected channel, and then showing the SCADA system components of the MTU, the IED, and the RTU. And this final document that is being modeled is the North American Electric Reliability Corporation Critical Infrastructure Protection document. It's also a standard, and this specifies the security key infrastructure components, in this case network communications. So as you can see, the control server as well as the IED and the RTU, which are electronic access points, utilize network communication to perform some of their tasks, and the secure sockets layer technique is intended to protect the network communication between these devices. Now that you can see all of the 4 different documents modeled together and all of the links together, we can see how it's pretty cohesively linked and combined within the ontology. So once we have this data modeled and contained within the ontology, we need to have a way to pull out and utilize the relevant knowledge. For this purpose, we used to use the Sparkle querying language. It utilizes the concept of links and relationships amongst entities to traverse the ontology and pull out what's relevant and interesting to the user. So this is giving an example starting with the security principle of integrity and then showing all of the different techniques that would be pulled out using this query. It's important to note that we're not expecting the users to code this themselves. We, in our future steps, hope to have some sort of graphical user interface that the user could select their options. It would be converted into a Sparkle query, and then would return in a human-readable format the relevant information. This next query is showing the documentation relevant to security techniques. Specifically in compliance, it's really important to know what security requirements you're looking at and where they came from. So this would be a really useful query to say, you know, I'm looking for all of the security techniques related to this specific area or this specific system component, and then I want to pull out where these came from. And our final query shown here is talking about different properties. Sparkle is really great because you can give it sort of generalized queries between different endpoints and say, find me the links between them. So in this case, we're asking for any and all links between the domain of the attack and the range of system component. And in this case, we filtered it to only show the targets property, but it would give you a ton of other properties as well. So as you can see on this slide, it's showing all of the domain attacks and what specific system component underneath the range that they would target. It's really important when building the ontology to understand that in software-intensive systems, the environment and the context that this system is being built in is really important. So as you can see, we have the universe of discourse, and within our problem domain ontology we're creating, we have a bunch of different entities across this universe that are relevant. So as you can see, we have goals and objectives, we have organizational entities, we have environmental context, business processes and other entities, and then system entities, and all of these are related to the software system and the practitioners. And one of the emphases of OntoArc-RE is to understand and make sure that your system takes into consideration where this is being built. And finally, the reason we chose to use our ontology instead of, say, like a database is that it's really well defined. It provides an unambiguous representation of different requirements, all synthesized cohesively together and very usable. It depicts common vulnerabilities and exposures. In addition, it's multidimensional, so you can represent different viewpoints. So for example, if you have an engineer versus a vendor or a manufacturer, you can have all of those different requirements and viewpoints represented and usable to the user, which is something that just reading from a document couldn't do. Finally, we also have link analysis, so you can identify interdependencies as well as missing or conflicting information among all of these diverse knowledge sources that are modeled in the ontology. A really common issue in security compliance is that you may have two different documents that either contradict each other or are missing information, so it's really nice to have a cohesive way to notice, hey, there are these two documents that are returning this information and it either contradicts each other or it's missing a piece or it's reliant on this other entity that you didn't realize. So having this all contained within a very specific way and really usable to the user is a great advantage of using ontology. Next, I'm going to hand the mic back over to Carlos, who's going to talk about our framework for software-defined networks.
Before we continue, I wonder if any of you guys have any questions with respect to the ontology. Okay, so let's move on then. So,
Carlos, I have, this is Rakesh from Oregon State.
Yes.
I don't know if Gabe Weaver is in the room there in Illinois, but he was working with some ontologies to represent cyber-physical models of the system. And I had to miss a couple of slides of Josephine's presentation. I had to step out for a call, but at least from the last pieces I caught, it looks like there is a connection there that either we could leverage what you're doing or maybe you could build on what we are doing. So it might be worth making that connection.
Absolutely, that would be really great, actually. Yes, we certainly want to leverage the experience actually from other projects.
I will see if I can bring Gabe's attention to this work, and maybe he can tell us more about how these are related.
Absolutely, that would be really awesome. We would really appreciate that.
Thanks. Yeah.
Okay, so let's move on to talk a little bit about software-defined networks. Well, the basic idea is depicted in this slide. We want to use SDN as a way to collect data directly from EDS infrastructure. in such a way we can forward it to our monitoring, security monitoring compliance framework. The idea is that, well, the normal traffic from EDS to forward control, for instance, SCADA, is going to go through SDN. And we're going to leverage SDN capabilities to redirect some of that traffic or to intercept some of that traffic in such a way that we can get information directly from network packets. Another example, another security and compliance requirement that we have extracted from the documents. This one, there's a requirement that says that PLCs and IDEs must not talk to each other. The basic idea is that you want to prevent IDEs from being compromised by an attacker that has control over a PLC. The security strategy here is inter-device communication between different, inside the network. Different attacks can happen. For instance, we can have the modification of a system configuration. We can have false information being distributed. Or we can have some instructions or some other stuff change. The security features in here is the implementation of a network security zone that can be actually realized by doing some network segregation of the network communication. And the components that are mentioned in this requirement are control network, IDEs, and PLCs. So this is an example of how the ontology is going to look like. We are not actually going into the details to explain every single component. Just a couple of things. Once again, we have the cybersecurity procurement language document serving as a base. Then we have different threats, in this case, inter-device network communication. There are several ways this can be attacked, this attack can be realized. And this communication targets two components within the SCADA system. There are PLCs and IDEs. And the segregation of the network is intended to restrict this communication between these two devices. Looks like Illinois is having some trouble. Hello? Somebody else there?
OSU is here and can hear you, Carlos.
Okay, well, I'll continue. Yeah, I'll continue. Sorry about that.
Yeah, I'm not sure about Illinois, though.
Yeah, that's really unfortunate. Well, we'll move on. So the basic idea is to have SDN serving as a platform for network communication. And, well, standards specify the PLCs should be allowed to talk to each other. And also, there should be a flow, a network flow between PLCs and SCADA, as you can see here in the green arrows. Another requirement we can see it in here is that IEDs should be also allowed to talk to each other and to SCADA as well. So we have a set of allowed network flows. But what the standard says is that, well, the direct communication between PLCs and IEDs shouldn't be allowed. So how are we going to be doing this using SDN? Well, following SDN architecture, we plan to have a controller, and then we want to have an SDN application running on top of the controller. And on each of the switches, we're going to have the switch tables. Now, the idea is that for all of the traffic, all of the network flows that are going to be allowed, we're going to specify those in a traffic policy. And following the SDN paradigm, eventually, we're going to be inserting some entries into the switch flows, into the switch table, in such a way that at runtime, all the actual flows that are allowed in the system can be carried on. In a similar way, we want to have the flows that are not allowed to happen, and we should also have some entries into the switch tables such that at runtime, the traffic flow is not allowed. In this case, we also instruct the switches to forward the offending packets all the way up to the controller in such a way they can be later forwarded to the SDN application that's going to be serving as a monitoring point. And this application can actually raise a flag when this kind of forbidden communication is detected in the system. So as you can see, there are many benefits of using SDN, and that's one of the reasons why SDN is getting a lot of attention in both industry and academia. With respect to EDS, we think that it's a solution that is customizable in the sense that we can implement several monitoring models as, in the form of SDN applications. It's not intrusive because we don't need to modify existing infrastructure. We don't need to modify SCADA or physical meters and so on. We believe also that it's scalable in the sense that new network nodes or new components can be added into the system. And finally, also a very important thing is it's expected to be platform independent. It means that we can support different components and different configurations. So this is what we've been doing so far. We are working in three things. First, we are working on the ontology engine. We have several documents on security compliance that already parsed. We have already, because you have some statistics on the amount of entities and relationships we have been able to create so far. We have some experience working on SDN as well. We have implemented a basic infrastructure, a proof of concept, network and tracker flow redirection, and we're also working on testing it and refining it. And now we're on a third step. We're working on implementing the overall backbone framework for our solution, and also we're working on a proof of concept model that can implement a compliance workflow based on the ontology requirements and can successfully leverage SDN. We are also working from partners in both industry and academia. I think the most important thing we want to do is that we want to get some feedback on real-world security compliance requirements and best practices. We really want to leverage experiences, use cases, information on the documents that people find relevant, and also some descriptions of some conflicts or some contradictory documents that exist out there. And later on, we would really like to implement one of these proof of concept software modules that can define or can depict a customized workflow based on the requirements we have been able to extract from the documents, and that can actually leverage as well data that is collected from real field deployments. If you can use SDN for this, that would be really awesome. But otherwise, if we can use real data, that would be really, really interesting. To finalize this really short talk, we have some plans for future work. As Josie mentioned before, we really want to make this really friendly for users. We want to support graphical user interfaces. And also in the future, we also want to implement, we want to extend this framework in such a way we can implement a model that can simulate attacks. And based on this simulation, we can study different security risks and different security assessments. At the very end, I think the ultimate goal of this project, as any other, all of the projects I think that are involved in GRETC, is to improve the public's confidence on EDS. So I think that's all from respect to the actual presentation. Now, we want to thank you for listening, and now we are ready to get your questions or comments on our approach. Thanks so much.